Good afternoon, everyone. Give a few minutes to let everybody jump on here, and then we'll get started. Okay, we'll get started here. So today's webinar is what you need to know, disinfection byproducts. A few housekeeping items before we get started. We are recording this webinar and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel, or you can email us directly. If you submit your questions through GoToWebinar, we receive a report with your question and your contact information, and we can follow up directly after the webinar if we don't get a chance to answer it during the webinar. If you're interested in receiving a PDF or a link to the recording of the presentation, please contact us at the email you see there. We encourage you to share the recording within your network. At this time, I'd introduce myself. I have worked at Carus for 25 years in the Technical Solutions Group. I conduct laboratory testing, product demonstrations for Carus municipal, industrial, and remediation customers and prospective new customers. Product demonstrations can include technical training, safety presentations, installation of safe chemical handling and dosage systems. My degree is in chemistry, ACS certified from Illinois Wesleyan University in Bloomington, Illinois, and I am a member of American Waterworks Association, Water Environment Federation, and the American Chemical Society. So to give you a brief outline of the webinar, which is going to last approximately 1 hour, we're going to talk about the permanganate products that you would use to help with disinfection byproducts. We'll then specifically get into where we currently stand with the disinfection byproducts rule. We'll then talk about some permanganate demand jar testing, so how you're going to go about establishing a dosage of permanganate to remove organics from the water prior to your disinfection. And then we'll go through multiple case studies detailing different applications and the results for both THM and HA reduction. So there's two main products that you can use in the case of permanganate when using it for disinfection byproduct control. Probably the one that most people are familiar with is Carus potassium permanganate, chemical formula KMNO4, and it looks like the two purple pictures you see there. So it looks like purple sand. Depending on the grade you buy, it will look more purple if it's a technical grade, and if it's a free-flowing grade, which is by far the more common, it's going to have kind of a grayish purple look to it. The free flow additive kind of dulls the color, but allows that product not to get as lumpy when you're feeding it. With Carus potassium permanganate, you're always going to see it in that granular crystal form. It is pretty dense, so about 100 pounds per cubic foot for bulk density. It is shelf life stable, and it does keep indefinitely if stored in a cool, dry area in closed containers. So with Carus potassium permanganate, a month from now, a year from now, 3 years from now, in a sealed container, Carus is still going to be the same 97 to 99% active as the day you bought it. So it doesn't decompose like something like hydrogen peroxide, which loses strength over time, or sodium hypochlorite, which would lose strength over time. Carus is going to keep the same concentration in that container. So you can buy product and store it on your site, and you can keep months to years of chemical on hand, or if you're using it for something where you only have to use it part of the year and you won't use it until the next season, you can keep that product over the year to the next season when you're going to need it. So with disinfection byproducts, typically they're their highest in the summer months. So we have customers that feed during the summer months, and then they don't feed during the winter months, and then they come back around and use whatever chemicals left over from the year before when they start their next summer season, and then purchase more at that time. Now, one of the things to keep in mind with Carus potassium permanganate, since it is a dry product, typically the easiest way to feed it is to turn the dry product into a solution and then feed that solution to your drinking water. So in the case of your raw water source, either at your intake or your wellhead, to feed it. A typical method of making a solution is going to be making somewhere between a 1% and 3% solution. Most of our customers make a 3% solution. The reason for that is the math works out pretty easy. It's a 0.25 or a quarter pound of permanganate per gallon of water to make up that solution. Now, there are various package sizes available. Most common are 55-pound pails, so they're a 5-gallon bucket, or 330-pound steel drums. We do have customers that are also on bulk and cycle bins, which are 3,300 pounds. One thing to keep in mind with dry Carus, I mentioned there's a technical grade and there's a free flow grade. The free flow grade does help prevent lumping, but it doesn't completely stop it. So in the middle of summer, like we are now with a lot of heat and humidity, if you open a package of permanganate and expose it to the air, the longer that sits exposed to the air, it will pick up moisture and humidity from the air and start to lump up. So one of the things you want to do is if you're making a solution, either use the whole package, or if you're only going to use part of a pail or part of a drum, you want to reseal that back up. So put the lid back on, make sure it's sealed, so you keep it from being exposed to all that humidity so you don't have that lumping. Usually what I would suggest to customers, or easier thing is to use all the package. If you're making a 3% solution, size your tank to use the whole package at once. So if it's a 55-pound pail, make sure that you have a tank that can take the whole pail at once when you're making up your solution, and that way you don't have to worry about partials. Same thing with the drum. Now, a little newer product, but still been on the market now for just about 20-some years, is Carus liquid permanganate. Chemical formula for that is NaMnO4. It's the white capped product you see there in the picture, very dark purple color, almost looks black when you're looking at it from the outside of the container in. You dilute it down, it's going to have the same distinct purple coloration though that Carus potassium permanganate does in solution. Now in the case of Carus sodium permanganate, chemical formula NaMnO4, you're always going to see this in the liquid form. So with Carus, you always see it in the dry form. Carus you're always going to see in the liquid form. Carus is sold at 2 grades, 20 and 40%. The shelf life for Carus though is the same as Carus. It will keep indefinitely if stored in a cool, dry area in closed containers. So if you buy 20% or 40% Carus today, a month from now, a year from now, 3 years from now, it's going to be that exact same concentration. So it does not lose strength. So we have customers that take bulk product in, and they might use a bulk tank over the course of a full year, and they see no degradation, no loss in strength from the permanganate that they're purchasing. And like I said earlier, with someone that might use permanganate seasonally, with liquid permanganate, they might bring in multiple totes this year and not use them all for treatment of their water quality issues. They can keep those totes till the next season and use them with no loss of strength. So, you just want to make sure you store them in a cool, dry area so they don't freeze, and they'll be usable the next year. Now, why the difference? Carus is always available as a liquid because when you change from the potassium ion to the sodium ion, you increase the solubility of the permanganate ion in solution. So that's why you're only ever going to see Carus and sodium permanganate in liquid form. The typical versions we sell are 20% and 40% out there in the market. So Carus is 20%, and Carus C, which stands for concentrate, is the 40%. Typical packages for this, we go as small as a 5-gallon jerry can, but probably more common is a 55-gallon drum or a 250-gallon IBC/tote, and then bulk. Now, one of the questions we get asked Is there a difference between potassium and permanganate and sodium permanganate? No. They impart the exact same color when you dose them into water. So in this case, this is a beaker showing you different concentrations of permanganate. And as you increase the concentration of permanganate in water, in this case, in these volumetrics, it's in distilled water, so the color will hold. You can see that at low levels, it looks almost clear, but if you were to put white behind it, you can see kind of a pinkish color. As you increase the concentration to 5, 25, 100, it starts to become more pink and then to a purple coloration, which is why the 20% and 40% concentration of Carus looks almost dark black. It's just really a dark purple color because the concentration at 20% is 200,000 parts per million versus what you see here of 1 or 100 parts per million. Now you'll hear people on the chemistry side of things use milligrams per liter or parts per million. Those terms are interchangeable when we're doing dosing in drinking water. So when we talk about a dosage, we might say milligrams per liter, but we could also say parts per million to mean the same thing. The other thing, besides the coloration of permanganate being the same, regardless whether it's potassium or sodium permanganate, the other part is all the reactions are the same. So all the chemistry, if you're removing iron and manganese, you're removing taste and odor compounds, you're removing organics that cause disinfection byproducts. Sodium and potassium permanganate is going to react the same way with all those constituents, and you're going to have the same oxidation reactions. So there's no difference. It's really a matter of what do you want to have on your site. Do you want to bring dry product in and have feed equipment to make it into solution and then feed that, or bring in a concentrated solution and feed that directly? So it's just a matter of preference at your site, how you handle your chemicals and what would be easier for your staff and your plant to use. Now, regardless of what type of permanganate that you're feeding, there is an industry standard from American Water Works Association, B603-16, and it lists both potassium permanganate and liquid permanganate, sodium permanganate, and has standards of what you would expect to see with your permanganate. So what's the quality going to be? Are there insolubles in the liquid permanganate? So how much sludge would you see? You should really expect to see very little in sodium permanganate. If you're using potassium permanganate, it talks about particle size, which would be, is it dusty? It shouldn't really be very dusty depending on the grade of product you're buying, and then also what the concentration, the assay of those products are. You can get that standard directly from American Water Works Association. The other standard that's really important is NSF Standard 60, which is testing it's done by the NSF group that certifies that permanganate can be added to a drinking water, and it establishes a maximum use level for both potassium permanganate and sodium permanganate that you're going to apply to a drinking water. So you want to ensure as a drinking water plant that you have a product that meets the NSF Standard 60, and it'd be nice if it also met the AWWA standard because that's a standard above the NSF of applying it to drinking water. Now, why would you apply permanganate? We're going to talk about disinfection byproducts, but there's a long list of things that permanganate's used for in drinking water. Typically, the original applications for permanganate in drinking water back 100 years when Carus first started was the very easy things, iron and manganese oxidation. So whether you're a groundwater or a surface water source, if you had iron and manganese, you could use permanganate to oxidize those, to form an insoluble, and then you would filter those solids out. If you're a surface water plant, you might have had some taste and odor issues. You might have some issues with the algae blooms that cause the taste and odor issues. And so permanganate is very good at reacting with the byproducts that algae put into the water. So it can remove those taste and odor compounds that make the water taste bad. It can also react with cyanotoxins and remove those from the drinking water. So if the algae bloom gives you cyanotoxins, permanganate can be used to remove those. Permanganate can help remove organics or react with them, which your then coagulation process removes. And we'll talk about that in much more detail for disinfection byproduct removal. Some other smaller applications, permanganate can be used. Some of the organics in drinking water can make the water have a color where it won't be clear. It'll have kind of a yellowish tint or a brownish tint to it. Permanganate can react with some of those organics. Some of them, like humic and fulvic acids, are very reactive, so they're very easy to react with permanganate and remove. And then after you filter the water, you'll have a very low color water, so it looks normal. And then in groundwater can be other issues like arsenic and radium that you can use permanganate or applications of permanganate to remove. So there's a wide range of things you can use permanganate, but today we're going to focus on disinfection byproducts. Now, one of the questions you may ask yourself, or you may already know, where do disinfection byproducts come from? So they're a combination of a disinfectant. Typically in drinking water, it's going to be free chlorine that we're applying at the plant, but it can be a combination of bromine or iodine, and then that reacts with the natural organic matter. So you have two ways you get natural organic matter. So you can have the original total organic carbon, TOC, that comes from the raw water source, or you could also have natural organic matter that's out in your distribution system in the pipeline. You might have some biofilms and some growth out in your distribution system, and so you might see some differences in the distribution system versus what you see in the plant. But it's the combination of that disinfectant plus the natural organic matter, and that reaction forms THMs, trihalomethanes, and forms haloacetic acids, HAAs. Now, when you go and do your testing as a water plant, there are a couple different things that they test for. So the rule is the disinfection byproduct rule, but they test for total trihalomethanes, so TTHMs, and these are the four that you'll see on your water quality report. When you get the lab report back, it'll list all four of them, and then typically it lists a total level as well. The total level is the one that you submit for if you're in compliance with the regulation. By far, typically when you look at that, the chloroform is the largest amount or the highest number that you'll see. The dichloro, the dibromo, the bromoform are usually much lower levels. Now, where would you see ones where you see more bromine? The water would have to have more bromine in the source water. So a lot of times places that have high THMs with bromine are going to be somewhere near the saltwater source. So are they getting saltwater intrusion? Are they near a saltwater source? They can typically see some more bromine, or if it's the specific aquifer that they pull from, they might see more. But generally, chloroform is the one that you see at the highest level. For haloacetic acids, HAAs, you'll see a total number. It'll be called the HAA5s, and these are the 5 that they test. You generally see a spread across these, but generally the mono and the di are the higher on the list. But as the current regulation stands, these are the 5 that are tested for, and you report the total number, the HAA5 number that you'll get on your report. Now, there are 2 rules that apply for disinfection byproducts. There was the original stage 1 rule called the disinfection and disinfection byproducts rule. And the purpose was to reduce exposure to disinfectants and their byproducts. You can go to the EPA website and look it up, but they have the original rule and then the justification for it. But what they have found was that high levels of disinfectants, high level of disinfection byproducts have been linked to cancer or increased rates of cancer and reproductive effects based on people drinking water with those exposure. Now, the stage 1 rule affected any water system that added a disinfectant during any part of the drinking water treatment process. So you're required, if you're a drinking water plant, to add chlorine or chloramines for your final disinfection for the distribution system. So this covered every water treatment plant in the US that was of a large enough size that they had to add a disinfectant. The original stage 1 rule set the maximum contaminant level for THMs at 80 parts per billion and haloacetic acids at 60 parts per billion. The sampling under the stage 1 regulation was samples were taken quarterly and you had a system-wide running average. So you averaged all your sites together in order to get in compliance. Now, this is an old rule, so systems were to comply with the stage 1 disinfection byproduct rule back in January of 2004. After the stage 1 rule, they applied and got the stage 2 disinfectant and disinfection byproduct rule. So this had a couple steps to it. When the rule initially came out, you had to do initial distribution system evaluation. So what this was a self-evaluation to identify locations with high disinfection byproducts in your distribution system. So the idea here was go out, find sites, and you're trying to target your highest disinfection byproduct sites out there in the distribution system. What the data showed when people started doing this initial distribution system evaluation was that sites that were the farthest away from the plant, the longest water age, typically had the highest THMs. So those were going to be good for sampling for THMs at those high sites, far away sites with long water age. HAAs, some of the data showed that typically HAAs would climb in the distribution system, and then at the far points, they might drop off a little bit. So the midpoint of the system, kind of your middle water age, might have the highest HAAs, and your far points would have slightly lower HAAs. Part of that was believed by biofilm scavenging some of the HAAs. You would lose some of them throughout the system. So what this did was a lot of sites used to have all their THMs and HAAs were pulled from the same sample locations throughout the system. After this evaluation, what it led to was some places had to split some. So they would have some TH sample sites and some HAA sample sites that weren't the same. But the idea was to try to find the high sites. The other big change for this rule was the locational running annual average. What this meant was you were going to monitor and meet the MCL at each monitoring location. So typically when you looked at your sites, based on the size of your system, you would have a site near the plant, some toward the middle of the distribution system, and some at the far points. So you'd be spread across all those different sites. The old way was you averaged all of them together, and if the total number across all the sites was below the 80 parts per billion for THMs and 60 parts per billion for HAAs, you were in compliance. Under the new stage 2 rule, each site has to meet the regulation by itself. This was called risk targeted monitoring, which meant that everybody in the system was getting water quality that was below the MCL. So everybody had water that was below the MCL, even though their numbers might be different. Everybody was at least getting water that was below the MCL, which under the old rule, some people near the plant had very low numbers, and some people at the far point could have had numbers above the MCL. This changed it to make sure everybody was at least under the MCL for water that they were drinking at their home. Now, there was a part of the rule that said if you had significant excursions, which means you had short-term peaks in disinfection byproducts that was going to cause a spike or cause you to have a violation, you were supposed to look at your operational practices, what you were feeding, what you were doing to make sure that those wouldn't happen, and then work with the state to identify actions to prevent future excursions. So this could be, we don't feed year round, and now we're going to feed year round to make sure the numbers are always low. Was it a coagulation issue and we need to do something to help with that side for organics removal? Basically, look at your water quality treatment process and determine what's the best way so that you've got kind of consistent results and you don't have spikes that throw you out of compliance. This rule was finalized in 2006 and had a very long time for you to be in compliance. The compliance with the stage 2 rule was that all systems were to comply with the stage 2 disinfection byproduct rule by July of 2014. Now, they're talking about a proposed new rule, and possibly the proposed rule will come out next year, but it's going to be the microbial and disinfection byproducts rule. It'll be an update to the stage 1 and stage 2 rule. It'll add some other stuff on the microbial side of things. It's right now in the stage where we haven't seen anything on it, but they're talking about it, and that proposed rule would come out next year as a proposal. And then typically after it's a proposal, there'll be about a year before it becomes the final rule, and then there'll be a compliance with that. They've talked about adding different disinfection byproducts. They've talked about changing how you test for them in the system. So all those things are kind of open as the EPA is working through them. One of the things that EPA has also said is that if you look at the number of rules that are violated by water plants throughout the US, there are 2 rules that stand out by far that have the most violations at drinking water plants across the US. So the 2 rules that have the most violations are the lead and copper rule, and the second most is disinfection byproducts. So when EPA looks at what water plants struggle with the most, it's going to be lead and copper and disinfection byproducts. Now, as part of a strategy for getting disinfection byproducts under control, there was a couple options that plants could take. The big one was, because it's a combination of the natural organic matter or total organic carbon reacting with chlorine, if you move the chlorine away from where you have the most natural organic matter, which would be the raw water, and move the chlorine to the back of the plant, you can see a huge reduction in disinfection byproducts if you're removing the organic matter in your coagulation filtration process. So first step typically was move your chlorine from the front of the plant to the back of the plant. And depending on your state, you could move that chlorine to just right before the filters, or in some states you can move it to right after the filters. What that does is your treatment process removes all that organic matter, your TOC number goes down, and so you have less stuff for the chlorine to react with if you move it all the way to the back of the plant. I've seen plants in my history here at Carus of 25 years see as much as a 40 to 70% reduction in disinfection byproducts just by moving that chlorine point all the way back to the back of the plant in a surface water plant. Now what happens is, if you do that, it delays your disinfection, so you need to make sure that where you're going to add your chlorine at the back of the plant, you're going to have enough disinfection credit time in your clear well, your water tower, your water tank to meet your disinfection credits. So as you move the chlorine back, you need to make sure that you do have enough contact time at the back of the plant to meet that part of the regulation for disinfection. But if you can, move it back as far as you can. Now, the other reason you fed chlorine at the front of the plant was it was used for oxidation. So it removed iron and manganese, it removed taste and odor compounds, it reacted with organics. Those are all things that are not going to be there, so you need to replace it with a pre-oxidant that's not chlorine based. So we're going to talk about pre-oxidation with permanganate, but EPA put out that there was really a couple different strategies you could take for pre-oxidation. Your options were permanganate, chlorine dioxide, or ozone to replace your chlorine at the front of the plant. Those all act differently than chlorine, so they don't tend to form THMs and HAs. In the case of permanganate, we don't form any disinfection byproduct. Our byproduct is manganese dioxide as a solid, which you then need to filter out with your filters in your plant. You apply permanganate at the front of the plant. We remove iron and manganese. We react with organics and can help coagulate some of those along with your coagulation process. We also would remove taste and odor compounds and cyanotoxins. Now, as you do all that pre-oxidation at the front of the plant, that means there's less stuff available at the back of the plant to react with your chlorine when you finally do add free chlorine at the back of the plant. So doing all that pre-oxidation at the front of the plant removes or reduces the chlorine demand at the back of the plant when you feed it for disinfection. Typically, this can get you additional disinfection byproduct removal. Sometimes it can be very low depending on the type of organics you have. Sometimes it can be quite a bit higher at 25% or more, depending on if the organics are reactive and you can remove them. Now, like I said, you're going to remove taste and odor compounds, iron and manganese, and because permanganate generates manganese dioxide, you're going to help with the coagulation process because you're going to form some solids that the coagulant can grab onto and form larger parts. Now, one thing to keep in mind, like I said, permanganate doesn't generate any other additional disinfection byproducts. Now, there are two other preoxidants you can use. You could use chlorine dioxide, but it has an additional disinfection byproduct that you have to test for, and that is chlorite. So when you feed chlorine dioxide, depending on the demand of the water, you might have an issue with chlorite formation, and you have to measure that on a daily basis and make sure you're below 1 milligram per liter as the MCL. A lot of plants that feed chlorine dioxide are trying to target below 0.8 milligrams per liter so they don't have a violation. In the case of ozone, you have a monthly MCL for bromate. That's formed from ozone reacting with bromine in the water, so that's another thing that you would test for. So if you do choose a different preoxidant than permanganate, they will work to lower your disinfection byproducts, but there are some additional things that you need to test for, some additional disinfection byproducts. One of the things in the new proposed rule is talking about adding other disinfection byproducts that can form from the use of chlorine dioxide or ozone in the water. And because they do form some other disinfection byproducts, they might add some additional ones you would test for if you're using one of those two constituents. So you've decided or you want to attempt to use permanganate for disinfection byproducts. Well, what would be the first thing that you would do? Well, the first thing you want to do is to do a jar test to determine how much permanganate you're going to feed at your plant, because that's going to determine how well permanganate is going to work. Now, when we talk about adding permanganate for disinfection byproducts, you're going to add permanganate because it adds that pink color before it reacts to the very front part of the process. So typically that will be either at the intake structure at your raw water source. So if it's a river, a lake, a reservoir, you would feed out there. That gives you a ton of contact time, depending on how far the water source is from the treatment plant. The other place you could feed is at the rapid mix or as the water enters the treatment plant. That gives you less contact time, and that only really matters if you're not right next to your water source, right? So if your raw water source is a couple miles away and you can gain 30 minutes of contact time, it'd be better to feed the permanganate first to get that reaction done, and then you can monitor for permanganate residual coming into the plant before you add all your other chemicals. A lot of plants, though, are built right next to their water source, so whether they feed at the intake or they feed at the plant site, it might gain them 60 seconds or 2 minutes worth of reaction time. So in that case, you can feed directly at the plant at the rapid mix. There, what you're going to do is permanganate's going to react, and you're going to use your time in your rapid mix and in your slow mix, where you're building your flock size. That's going to be time that you're going to use as well for your permanganate reaction. So we do need, because of organics reacting a little slower, we do want some reaction time. So typically we want a minimum of 15 minutes, and ideally somewhere in the 15 to 30 minutes of reaction time to react with those organics, plus everything else that might be in the water. Ideally, what happens though is after you exit the slow mix / flocculator area, you see very little residual going into your sedimentation basins, because at that point we want the permanganate to be from purple to brown to have formed all that manganese dioxide. The manganese dioxide, along with the coagulant, settles out in the settling basin, and then you get very clean, clear water going to the filters, and that can be where you add your first dose of chlorine right above the filters, or if you don't have to add it there, you add chlorine post-filter. But the idea being that after you've gotten through the sedimentation basin, all those solids, including organics, have dropped out. So you have very clean water going to the filter, and so you can dose chlorine there or after it. So what affects the jar test? So one of the things with the jar test, especially for disinfection byproducts, is this is a test you're going to want to run at your site, in your lab. So you want to collect the sample and run the jar test as soon as you can after you've collected the water. So what concentration, what type of oxidizables do you have in the water? So do you have iron and manganese? Okay, that's going to be very easy to establish. In the case of iron, 1 part of iron requires 1 part of permanganate. In the case of manganese, 2 parts of permanganate are required for every 1 part of manganese. So you can give yourself a baseline dosage just based on how much iron and manganese is in the water before you even start the jar test. Taste and odor compounds, organics, are why you run the jar test, because you don't know how reactive they are. So what you're going to do is you're going to dose the jar with different amounts of permanganate and come back after your reaction time that you have in your plant and then measure the residual to see how much permanganate was consumed. The jar test can take that time into account. So whether you do the jar test for 15 minutes, or you might do a jar where you do it for 15 minutes and then you come back in 30 minutes and an hour to see how much the demand increases over time. So are you still seeing a lot of reaction, or has the reaction really slowed down? The jar test takes into account temperature. Nothing changes because you've just got fresh water when you're doing it. And then you can keep track of pH and things that you're doing in the jar test. What you can see here in the picture is low concentration permanganate kind of looks brown. The raw water, which is all the way on the right, is kind of yellowish to begin with. And then as you increase the permanganate dosage, it starts to take on a pink to purple coloration as you increase the dosage. So visually, you can see what's going on. Like I mentioned, application point typically intake or as far ahead as the rapid mix as possible so you can get contact time, but you can take that contact time in the flocculators. For disinfection byproducts, we typically want to talk about having 15 minutes of contact time. More could be better depending on how reactive your water is. but you want at least a minimum of 15 minutes to get some reaction prior to you adding all your other chemicals, or 15 minutes with the other chemicals added so that you still get them doing their benefit. Now, why would I say not to add carbon, polymers, or chlorine at the same point? In the case of carbon, carbon can absorb organics, but carbon also absorbs permanganate and neutralizes it. So if you feed the two at the exact same time, what's going to end up happening is some of your permanganate is going to absorb onto the carbon, and so you're going to lose some of your permanganate to reaction, neutralization reaction with the carbon. And as that carbon reacts with the permanganate, you lose some of its ability to absorb organics as well. So in that case, if you separate the two out, it's more efficient use of both chemicals. Now, in my 25 years at Carus, I have seen many, many plants that feed carbon and permanganate right on top of each other. They don't have any other way to do it. They're all added at the rapid mix. The only thing is, it's just not as efficient. Just know you're going to consume some of your carbon and some of your permanganate from the reaction between the two. Now, polymer/coagulants, why would you not add them at the same time? In the case of polymers and coagulants, if you add them later in the process, after permanganate is formed manganese dioxide, you might be able to tweak your coagulant and polymer dosages down because you're already forming solids and you won't need as much to get good floc formation. If you feed them all at the same time, you typically don't see that benefit, so you might feed slightly higher dosages of your coagulants or polymers if you're feeding everything at the same time. Lastly, with chlorine, in the case of organics, if they react with chlorine to form THMs and HAAs, that's a one-way path. Once you form the THM and HAA, it's no longer reactive with permanganate or any of the other preoxidants. So if you're feeding chlorine dioxide or ozone, once you form a THM or HAA, you can't oxidize it, it's there. So the idea here is move the chlorine away from your preoxidation because you don't want it forming THMs and HAAs that you can't remove at that point. Move it to the back of the plant so that way you don't have it causing an issue for you. Ideally, when you feed permanganate, once you're feeding it in the plant, carry a slight residual either into your rapid mix or to the end of your flocculators if you're feeding in the plant so that you know you've maintained permanganate residual for that set amount of time that you have. Now, the jar test we talk about is the permanganate value over time. And this takes into account all those things. What's oxidizable, what's the temperature of your pH, what's going on in your water at that time. You'll take that water, split it into the jars. Typically, most jar testers have 4 or 6 jars. I typically will use 3 of them for dosages, and 1 of them is just a blank to see what the water does by itself. Dose somewhere between 0 and 3 milligrams per liter. In drinking water, typical dosages are usually somewhere between 1/2 to 1.5 parts is typical, but some waters can be very reactive, up to 2 or 3 milligrams per liter. Come back after your detention time, so you've determined from your intake to your plant is 30 minutes. Show what the reaction would be, and then come back to those jars and measure permanganate residual. How would you go about measuring that permanganate residual? So in this case, the easiest test method is the DPD free chlorine test method, sold by Hach and other companies. You do need to filter the sample first to remove solids. So we're doing this in raw water, which has solids, so we need to filter it to remove those. You add the powder pillow. It's going to react and turn the same color as it would with free chlorine. So it's going to turn red, and the darker the red, the higher the permanganate concentration. One thing to keep in mind is if you've got chlorine in the water or ozone or chlorine dioxide, those all show up on the powder pillow test. So you really want to use this test when you just have permanganate and nothing else in the water, because then you'll just measure the permanganate concentration. I can't stress enough, you need to filter. This test method, with the addition of the powder pillow and the solids in the raw water, you need to filter the sample prior to adding the powder pillow to remove all those solids from the water so that you get just a reaction between the permanganate and the powder pillow and none of those solids that are in the water. We typically in the field use 0.22 micron filters. You can use 0.45s as well. You just want to make sure that after you filter it, you don't see any solid content in the filtered water. You add the powder pillow, and like I said, it's going to turn red exactly like the free chlorine powder pillow. Now you're going to ask, we're using it as a free chlorine powder pillow. Why can we test for permanganate? That powder pillow reagent reacts with any oxidant, and permanganate's an oxidant, so it turns colors. The difference is, because the powder pillow is set for chlorine, your reading on the instrument is going to be slightly off. In the case of potassium permanganate, you're going to multiply your reading by 0.89, and that will give you what your actual reading is as potassium permanganate in solution. In the case of sodium permanganate, the math's a little different. It's 0.8 times your reading. So just keep in mind your DPD reading that you get is going to be a slightly higher number than what the actual concentration of permanganate is. And that's just because of the difference between how permanganate reacts with the reagent versus chlorine. In the case of this jar test, it was a surface water plant. They had 15 minutes of contact time from their lake intake going into their plant. So the jar was set up, dosed at various levels. In this case, used all 6 jars, so 1, 2, 3, 4, and 5, and came back after 15 minutes and measured the residual. And what you get is a demand curve in this case. Where the demand curve goes down and intersects the axis is what the actual demand would be for the water without having the higher dosage. So in this case, a 15-minute demand for this water was showing you would consume about 0.4 milligrams per liter of permanganate in 15 minutes. What this jar test allows you to do is, now I know in my plant I need to feed 0.4, and then if I measure it 15 minutes later when the water's coming into the plant, I should be at just about 0 residual. So it gives me my dosage for that 15 minutes and how much I should feed, and then I can do monitoring in the plant to make sure I don't have excess residual coming in based on water quality shifting. Like I said, you could then extend this and maybe do a 30-minute demand to see what does that number go to. At 30 minutes, it might go up to 0.8 milligrams per liter, which tells you the water is still pretty reactive. So you're still getting quite a bit of reaction because it's just as much in 30 minutes. It doubled in 30 minutes versus 15. Or it might only go up to 0.5 or 0.6, so it's a very small change. So you've got a much slower reaction going on. This is just to give you a basis of what to feed in the plant. So once you've established with the jar test what the dosage should look like in the field, you can take that data and go to the plant and run a plant trial and generate some data. What you're going to see here in case studies are multiple different applications of how they fed. Our first case study here was a groundwater plant, but it was under surface influence. It was a unique treatment process because it was an active flow, which is sand ballasted coagulation. So they treat water and filter it in a very small footprint before they go to filtration. So typically there's not much contact time in the plant. They're not the standard flocculators with 15 or 30 minutes in a settling basin with multiple hours. In this type of plant, typically from the front of the plant to the back of the plant, there'll be 15 to 20 minutes of full contact time. What they were seeing was they had manganese that would vary based on the surface influence. And they also had THMs above 80 because they were initially started the plant up with free chlorine at the front of the plant, and they were hammering it with free chlorine to try to get the manganese to oxidize, but they were reacting with all the organics to form tons and tons of THMs. So they wanted to lower the manganese to below 0.05 in less than 10 minutes, and they wanted to not form THMs in the front part of the process. So you can see their infiltration wellheads there, the 3 gray boxes, and then that mound of dirt with the fence on it, that's a river that's running nearby. So they're getting direct influence by the river. So they are under direct surface influence, which is why the manganese level would vary coming into the plant. Their trial equipment, because the plant was initially designed with free chlorine, and it wasn't until they started running the plant that they noticed that the THMs were through the roof, and they were going to have an issue with them. They did a temporary setup with liquid permanganate with a pump on top of it. Because those wells were directly outside the plant, there was no benefit from feeding at the wellhead to in the plant. You were only going to gain about 30 seconds of contact time. So they fed at the flash mix. And the way we did this is we taped an injection quill line down to hold it to the bottom of the flash mix. And then you can see the pink coloration coming over as it splits into two active flow processes. So permanganate added along with their micro sand, along with their coagulant and their polymer. The idea being all that stuff reacts, and the permanganate doesn't react with the coagulant or polymer or the sand, but we react with the manganese, we react with the organics, and then all those solids we generate stick to the sand, and then the sand drops out in the active flow process. Then it goes to lamella separators, and then finally to the finished filters at the back of the plant, water entering the plant and leaving the plant in less than 30 minutes from front to back of the plant. So prior, when they were feeding chlorine, they were above 80 parts per billion in the clear well for their THM, so they're in violation of the stage 1 and stage 2 rule. And they were still having issues with the manganese only getting down to about 0.12. So when they initially started the plant up, they were getting some of the manganese to oxidize with chlorine in the 10 minutes of contact time in the plant. But then in the clear well, as the water sat with additional chlorine, it would start to turn yellow and they would get more manganese drop out, and the last bit of the manganese would come out in the clear well, which was bad because obviously you're dirtying up your clear well, you're going to send that out the door. With sodium permanganate to replace the free chlorine at the front of the plant, we dropped the manganese in the filtered water down to about 0.02, so very low level going into the clear well, and then they added their chlorine going into the clear well. So water that entered the clear well had no THMs. It was at 0 before they chlorinated it. And then they had their disinfection time in the clear well prior to going to the system, and were well below the THM standard leaving the plant, and very low levels out in the system. So they're able to remove everything in the plant and not have that issue of violating the disinfection byproduct rule leaving the plant. Another case study here, this is THMs. This is Elsinore Valley out in California, 37 MGD facility, THMs in the 130 to 140 out in the distribution system, and they were getting fishy, musty odor complaints, about 5 to 10 per month. Their water, pretty reactive, 2 to 3 parts of permanganate to react with all the stuff that was in the raw water source. Their trial was two-step. We're going to move the pre-chlorine from the front of the plant and move it back to right above the filters. And we're going to apply permanganate at the front of the plant. So prior with chlorine, you can see they added chlorine at the flash mix. Immediately, we're at 38 parts per billion through the flash mix. Going into the settled water, we're at 60 parts per billion, so almost at the 80. Filtered water, as it passed through all the settling basins into the filters, was at 130, so we're well over the 80 part per billion. Clear well at 140. With the change to treatment, no disinfection byproducts formed, so THMs are at 0 in the flash mix and the settled water. When they added to the filtered water chlorine, we got about 35 parts of THMs. And then after the clear well, you're at 40. So you're at 40 going out to the distribution system, so half of what the current regulation is. So a very big reduction. That chlorine plus the permanganate, 70% reduction. The other part they noticed when they fed permanganate in place of the chlorine at the front of the plant, those musty, fishy odors went from 5 to 10 per month all the way down to 0. So completely removed all their taste and odor complaints from the system. So the combination treatment was much better with permanganate as the preoxidant and chlorine at the back of the plant. Another case study here, this one's specifically looking at HAAs. This was the Southern Illinois surface water plant, about 4.5 MGD. And their HAAs, depending on the time of the year, could be anywhere from 14 to 150 parts per billion. So their goal was they would have loved to be below 30 parts per billion, so half of the 60 part per billion regulation. They were going to move the initial chlorine feed point, and then they were going to evaluate chlorine dioxide versus permanganate as preoxidants, and then also investigate using powder activated carbon to absorb the THMs and HAAs after you form them with free chlorine at the front of the plant. So as they did this study, they noticed that, and they knew, their HAAs increased as water temperature increased as they got from spring into summer. You can see here from May to August, their HAAs climb. So early May, they're low, 20 parts per billion. By June, they're up to 45, and they continue to climb. They started to feed permanganate in place of the free chlorine and move it to the back of the plant, and you can see the levels dropped. They increased the permanganate dosage, which is the blue line, and that forced more organics out of the water that were reactive. So you can see in August, the number continued to drop and continue to drop. What they found was all the products would work. So they could use potassium permanganate as the preoxidant. They could use chlorine dioxide as the preoxidant. They could use carbon as a way to absorb the HAAs after they worked. They would all work, but based on their testing, permanganate worked the best for them because it removed iron and manganese, it removed taste and odor compounds, and it got them to the target, the lowest dosage at 1 milligram per liter. Chlorine dioxide had a similar dosage, but was more expensive on a usage basis, and carbon also reacted as well. And carbon is cheaper, but you'd also have to feed pre-chlorine at the front of the plant. So what they chose was they used permanganate as the preoxidant, and chlorine got moved to the back of the plant. THMs and HAA formation went down, taste and odor complaints went down, continued control of iron and manganese. One other thing they did notice was that floc settling and coagulation improved with the permanganate at the front of the plant because we were forming manganese dioxide that helped with some of their coagulation in solids. Our final case study here, Disinfection By-Products. This was a southern water plant, 20 to 40 MGD, surface water from a river. They wanted to move pre-chlorination to above the filters, and they wanted to apply a kind of a target dosage of 0.5 milligrams per liter of sodium permanganate at the river intake. Now, the river intake was right next to the plant. You gained a couple minutes, but then they used the reaction time in the plant as well. So the initial setup here was they were trying to find solutions, and they wanted to look at two test times. They wanted to look at winter when the water was the coldest and their THMs and HAAs were the lowest. So they ran a winter test in January and February of the year. And you can see that their numbers are pretty low for THMs. At the plant, 20 parts per billion, and then out in the distribution system, they're in the 50 to 60 range. HAAs at the plant are 15, and then in the mid 30s going out to the plant. So their system average and their individual sites all pass the stage 2 and stage 1 regulation in the winter months. Turned on permanganate, those numbers lowered in the winter months, which was their cleanest water. So the averages dropped. So the THMs dropped from 48 to 34, the HAAs from 28 to 14. So you were even seeing a reduction in the cleanest water, the lowest numbers in the winter months. So about a 30% reduction in THMs and about a 50% reduction in HAAs. They returned and did the test again in July and August of the same year, this was when they had the worst numbers going out to the system. Saw the same thing. There was a reduction between pre-chlorination and sodium permanganate at the front of the plant, with the pre-chlorine now being right above the filters. You can see the numbers are quite high. So everything that's flagged red would be above a standalone 80 parts per billion or 60 parts per billion. But remember, we're averaging 4 quarters together. So this would only be 1 quarter. You'd get to average it with 3 other quarters. But what we saw was this was their highest 2 months for THMs and HAAs in the system every year, based on history. We were still seeing about a 30% reduction in THMs by the change, and HAAs were going to be reduced by about 60%. So it got a little bit better in the summer months for HAA reduction. Combine those 2 quarters together, so that's 2 quarters versus 4 quarters. You can see that across the board, each of the individual sites were going to comply with the 80 part per billion and 60 part per billion part of the regulation. If it was pre-chlorine, this is why they were having failures with stage 2. A lot of the individual sites were going to be over the regulation. So based on this data, what they looked at was, do we need to feed year-round? Do we see a benefit year-round? Well, clearly there's a benefit in the summer and the winter. We're still seeing the same amount of reduction. It's just how much does that reduction mean number-wise? When it's 30% versus a number that's at 100 parts per billion, it's a significant reduction versus in the winter months where that same 30% reduction might be only a reduction in 10 parts per billion. What this meant was their initial setup was, we're going to feed during our 2 highest quarters. So they fed in the spring and the summer when their THMs and HAs got the highest. And that has been their treatment plan for years. They start feeding in April, May, and they stop feeding usually September, October. So they feed during those 6 months in the middle of the year when their HAs and THMs are the highest. And then they switch back to pre-chlorine at the front of the plant during the winter months when their numbers are low. And based on that, they can meet the stage 2 regulation by shaving off all those peaks in the spring and summer months. They were able to reduce the chlorine during the summer months, moving it to the back of the plant and feed the permanganate. Some things that the operators were concerned about, would we be able to control iron and manganese and taste and odor? What they found is they were able to measure permanganate residual, make sure all the iron and manganese and taste and odor compounds were gone. They typically measured residual going into the settling basins at the plant, and so they could maintain permanganate, feed the right amount, and make sure they didn't have excess, and keep good control over the plant based on that feed system. To finish up here, drinking water has been used permanganate for over 100 years around the world. Doesn't matter whether surface water, groundwater, whatever the application may be, specifically you want to target the contaminants you know permanganate reacts with. One thing to keep in mind when you do use permanganate, you need a treatment plant with clarification and filtration. Permanganate's going to form manganese dioxide, which is a solid, which that solid needs to be filtered out of the water. So in groundwater, a lot of times it's add permanganate to react with iron and manganese and then directly to filtration to remove it. In a surface water plant, you're going to add permanganate, form manganese dioxide, and then your coagulation polymers will coagulate those solids, and then your filters will remove them. If you don't have filtration, you can't add permanganate because you're going to put those manganese dioxide solids out into the distribution system. You're going to have dirty water. It's not going to work. Doesn't matter, very small systems, very large systems can all use permanganate depending on the contaminants they have to remove. Besides getting in compliance with the disinfection byproduct rule, permanganate can also remove tastes and odors from the water. They can react with some cyanotoxins to remove them from algae blooms. If it's colored water from organics, that's another thing that reacts with permanganate. And then obviously iron and manganese removal as well. Overall, when you feed permanganate, what you're trying to target is to get overall better water quality at the end of the door, going out of your plant to the customer at their tap in their home. And with that, there is my contact information. There's my phone number and my email address. And we'll take a few minutes here to see what questions I have. So in the one case study, the question was, how was the 0.5 milligrams per liter determined? So the 0.5 was determined with a jar test. So based on the raw water coming into the plant, the jar test showed for about 30 minutes of contact time that they would need to feed about a 0.5. So that was the way to establish the dosage in the winter month. And then that dosage was reconfirmed in the summer month, and it actually climbed a little bit in the summer month. One thing to keep in mind when you're doing the jar test is how much reaction time do you have? So in their case, they used all their reaction time in that case study. So from the river intake, which was only about a minute before it hit the plant, they used the 30-minute contact in their flocculators to get the reaction to go, and they measured residual going into their settling basins. So as the water exited the last flocculator, they measured, and their target was about 0.1 milligrams per liter going into the settling basins. Through the settling basins, they had about another 3 to 4 hours before it hit the filters. So the jar test was where we got that 0.5. So they were a low dosage, not a very high dosage. Like you saw in one of the other case studies, the jar test was showing 2 to 3 milligrams per liter with the California case study. So it's really, the jar test determines where you're going to start based on how much permanganate's there. With that, I'll thank everyone for your time. Please feel free to reach out, email directly. We can send you a copy of the slides and a link to the recorded webinar for you to share amongst other people in your network. Thanks.